Hello and welcome to section 9.5, where we want to begin the discussion on parametric equations. We take a look at a parametric equation that consists of plane curves. It says suppose that t is a number on an interval I, and then we have what we call a plane curve is a set of ordered pairs, that's x and y, where x is f of t and y is g of t, for the interval t is equal to in the interval I. So because we actually have a t interval here rather than an x interval, we define that as a parametric equation, which gives us a variable of t that's called the parameter. So our equations are x is equal to f of t and y is equal to g of t. So as we begin to graph parametric equations, we want to look at some values of t on a given interval, and then for each value of t we use the given parametric equations to compute the x and y values, and then we plot the x and y values on a smooth curve. So let's take a look at this particular example here. We have two parametric equations where x is equal to t squared minus 2t plus 1 and y is equal to 3t, and we want to look at it from the interval -3 to +3. So as we plot some x values here, we end up with 16, 9, 4, 1, 0, 1, and 4, and then we plot some y intervals. All we're doing is just substituting these values in for t. You should be able to do that with no problem. And then we use these values to determine the x and y point, where we have 16 and -9, and then we have 9 and -6, we have 4 and -3, we have 1 and 0, we have 0 and 3, 1 and 6, and then 4 and 9. So once we determine these intervals here, we can then plot these intervals on a particular graph. And so if we plot some points here, and I'll just put a few points, we have 16, which is out here somewhere in -9, so we have a point down here. We have 9 and -6. Looks like we have 4 and -3, and 1 and 0, and then 0 and 3, and 1 and 6, and then we have 4 and 9, and so forth and so on. So we have a curve of a parabola that opens up to the right. That looks something like this, and it continues on out. So this is the graph of those two parametric equations. We can also graph parametric equations using a TI. So let me bring up the TI and show you how to graph those parametric equations here. Before we do it, we must first switch to the parametric mode. So if we go to mode here and we highlight parametric and we switch to the parametric mode, let me drop this out so you can see this, and then from there we can go y equal, and notice that our y equals have now changed to x and t's. So if we plug in the actual x equation, which you're going to still hit the x button, but it gives you a t now, and we square that, minus 2t plus 1, and then we'll move to the y equal. The y is going to be 3t, and then I'm just going to do a zoom standard, and so that's the graph of that particular equation there. So you can see the parametric graph here of that particular equation. So let me bring out my parametric. Just bringing up a few slides so you can actually take a look at my graph. So I'll highlight a few things here. Parametric first, make sure you're in the parametric mode, and then there are your x and your y's, and then your graphs there. Alright, we can also eliminate what we call the parameter t and by using the substitution method, and once we eliminate the parameter t, we're back to an x and y variable, and we can go from the x and y variable. So let's take a look at how we eliminate. If we have parametric equations, x is equal to the square root of t, and we have y is equal to 1/2 times t plus 1. Our first step would be to solve, take x is equal to the square root of t, and we want to solve this for t. So we'll square both sides, so we end up with t is equal to x squared. And then our second step would be to substitute. We take the equation y is equal to 1/2 t plus 1, and we'll substitute x squared in for t plus 1, and then we can graph the function. And in this case here, we'll graph, and we can put this one in our regular. This becomes a function now, and we can graph it from x is greater than or equal to 0. So we'll graph this particular equation here, and you can see the graph of this particular equation from x is greater than or equal to 0. We want to follow the steps to eliminate the parameter here. Our first step would be to solve. We can actually solve for t. So we solve this for t here. T squared minus 2t plus 1, and we'll just subtract 1 on both sides. T squared minus 2t is equal to x minus 1. I'm going to complete the square here. T squared minus 2t plus 1 squared is equal to x minus 1 plus 1 squared. So I have a perfect trinomial here, and this will be t minus 1 quantity squared is equal to x. So I take the square root of both sides. I get t minus 1 is equal to the square root of x. So t is equal to 1 plus the square root of x. And then I take that particular equation and I substitute it in place of t in the y equals equation. So y is equal to 3 times 1 plus the square root of x. So I get y is equal to 3 plus 3 square roots of x. So I can use this equation now because it's a function in terms of x and y's, and I can use this equation to graph the function without the parameter. Alright, let's sketch the curve of this particular equation here. The first, by eliminating the parameters. So the first thing we're going to do is we're going to take x is equal to 3t plus 1, and we're going to solve it for t. So we end up with t is equal to x minus 1 over 3. And then our second step would be to substitute. Y is equal to 2 times the square root of x minus 1 over 3. So once we substitute in, we can actually graph this equation by plugging in values, and we'll let x be greater than or equal to 0. And so if we let x be greater than or equal to 0, we know that if we put in a value of 0, we're going to get a negative number. We put in a value of 1, we get 0. So we're going to start at 0, and we'll end up with a half of a parabola that opens up to the right. So you can graph this as a function in terms of x and y's, or you can graph this as a parameter in terms of t. Okay, let's look at a parametric equation that deals with a trig function, sine and cosine, and we know from the Pythagorean theorem that sine squared plus cosine squared is equal to 1. So what I would suggest here is our first step would be to take x is equal to 3 cosine of t, and we're going to solve this for cosine squared. So we have cosine of t is equal to x over 3, and if we square both sides, we're going to have cosine squared t is equal to x squared 9. And then we do the same thing for the sine. So we have y is equal to sine of t, and so we square both sides, we'll have sine squared t is equal to y squared. And then from that we can use the Pythagorean theorem and we can substitute these values, and in place of sine we'll have y squared. In place of cosine we're going to have x squared over 9 is equal to 1, and what we end up with here is an ellipse, and we can graph the ellipse, and a here is going to be 3, b will be 1, so we're going to have an ellipse with the major axis along the x-axis, so it'll be 3 and 0, negative 3 and 0, 1 and 1, and then we can actually have our elliptical equation here. Now I also want to show you that you can graph the parametric equation, and let's see if we can I'm going to bring up the calculator here, and we'll go to y equal. I'm still in the parametric mode, and so we're going to let x equal 3 cosine of t, and we'll let y equals the sine of t, and let's graph that function. So there's your ellipse there. So you can see it's probably easier in this case to graph in parametric for an elliptical shape or for a conic than it would be to graph in rectangular form, because if we're going to graph in rectangular form we have to solve this for y, and then we'll have a plus y and a minus y. You get the same equation, but it may be just fairly equal there, or easier. Alright, as we begin to look at parametric equations for a function, we need to make sure that y is equal to f of x and x is equal to t, and then in this case y is equal to f of t. So if we substitute t in place of x, we need to make sure we get the function y here. So that's the question: can you start with any choice for parametric equations for x? And the answer is no. The substitution must be a function that allows x to take place with all of its variables there. So in this case here, if I look at this example and I begin to substitute, so I said x is equal to t, so if I substitute x in place of t here, I get y is equal to 16 minus t squared. So that's parametric equation will work because it gives me x and t's are interchangeable here. If I substitute t plus 1 in this place here, I'm going to get y is equal to, and I think it's a negative t squared minus 2t plus 15, so that's not going to work. If I do the same thing here, I get y is equal to a 16 minus t, so that's not going to work either. And then if I do the last one, I get y is equal to 16 minus a t to the 4th, so that's not going to work. So you must make sure that f of t and f of x is equal in order to substitute parametric equations. So let's look at advantages of parametrics over rectangular shapes, and this is what I just originally told you in our previous slide, where if you have a conic and you want to graph a conic, it's probably easier to graph the conic in parametrics rather than rectangular coordinates. And so this shows an example of that here by graphing parametric equations versus rectangular coordinates there. Make sure that you're in a radiant mode and a parametric mode. And here's a kind of a word problem, actually a multiple choice problem. I'm going to find an example of a conic by eliminating the parametric. So here we can substitute in, and we can use the Pythagorean theorem, and we'll find out, or the Pythagorean identity, and we'll find out that our answer choice here should be D. And I'll let you work through the math on that one. And then we have this particular problem here, and if we want to eliminate the parameter and graph the function and find the vertex, we're going to find out that the vertex here will start at -1. So this concludes our section 9.5 on parametric equations. So you will have an assignment with this particular section, and if you have any questions, please feel free to email me. I'm signing off. Thank you.